Welcome back, everyone. We'll continue with Professor Teeth's lectures, second on the day.
Yeah, thanks. Okay, so let's continue on our discussions. We were doing linear perturbation theory, and what we realized is in the linear regime, now we will only be talking about matter perturbations. We won't distinguish between dark matter and baryons. And we also saw that we can write the perturbation as some function which grows with time and some spatially dependent function which basically gives you the field configuration. And at all the points they grow in a similar way. For like future convenience, what we will do is we will go to the Fourier space. We did it while doing the baryons, but we could have done it for the dark matter as well. So nothing will change except these ones will now be function of k. And the growth will remain the same. Okay. So you can just see that the equation basically remains the same, and you solve it, you get this one. So our observable quantity is the power spectrum. Now I will define power spectrum in a more like mathematically rigorous way, maybe tomorrow or the day after, most likely tomorrow. But it's a quantity which is essentially delta m, maybe measured at today, function of k square. I will put it a proportionality constant because there are other things which are hidden here. Those are constants, so I have put a proportionality factor. So it's a mod square of this quantity, and that is the quantity I had shown you in one of the slides. You remember something went up and came down. This is also a quantity which will be predicted by, for example, models of inflation, which tells you about how these initial conditions were generated at very, very early times. Now, again, I mean, if you have done inflation, separate matter, but if you haven't, what happens is many of these models will predict something which I'm calling P primordial of K, as if it has been kind of set at very early times at primordial epochs of our universe. It will predict something which looks like this, ns minus 4, with ns, which is a power, which basically is determines the power law index, is very close to 1. Present observation says 0.96 or 0.9 something. Okay, I forget the exact number, but close to 1. So this is that famous scale-free power spectrum. Now suppose inflation or whatever set up these initial conditions predicted something like this, and if everything evolved the way we derived, then today you would have seen a power spectrum which looks something like this, right? So if I had plotted PMK versus K. But clearly it did not look like that. Okay, it looked something which did like this. So what happened? Okay, so that is something we need to discuss, and I will discuss it very briefly. Yeah. Okay. So yeah, so again, when we do power spectrum, you will see something where instead of this quantity, what matters more is this k cube p of k, and why I will tell you in the next class or next to next. Okay, so that is the main reason. Yeah. This one, primordial. Okay. Yes. So what happened? Now you can almost guess what are the things which would have made these changes. Our approximations clearly broke down. Okay. Why did it break down? there are clearly two reasons because of which it broke down. After inflation, or whenever these initial conditions were set, the universe went through radiation-dominated era. In the radiation-dominated era, the component of the universe is dominated by radiation. So clearly, for example, the Poisson equation we wrote was for what? For non-relativistic matter. That was the assumption. So that Poisson equation was not valid, okay, if we have to include radiation in that. Number two, many of these scales would have been kind of larger than C by Hz at those early epochs. Okay. So these are the two things. And as I said, I mean, if the scales are much larger than the horizon size or the Hubble radius, then whatever we did was not valid. So because of these two reasons, this thing kind of, this feature arises. Of course, now to actually work out this feature, we have to go back to the relativistic theory and work out the linear perturbation there. And it is done, okay? It is done in most textbooks. And even if you look at the lecture videos I shared with you, I mean, there also you will find discussions on this. But here, rather than spending too much time going into that, what we will do is we will try to motivate this form through some heuristic arguments. So let us see what to do. So firstly, let's talk about what happens in the radiation-dominated era. So what we will do is we go back to our linear perturbation equation and write it in this form. It's 2a dot by a delta m dot. This remains the way it is. On the right-hand side, if you remember, there was a term, the driving term, which was also delta matter. Okay, delta dark matter, I mean, we wrote for dark matter. Now I'm saying that is not valid because the driving term is because of gravitational potential. And that gravitational potential is now driven by something else, not matter anymore. So let us write down, let us not use the Poisson equation, but let us just write it down in terms of the gravitational potential. So if I did not use the Poisson equation, you can show that this is the equation you would have written. And that will basically be minus k square phi by a square in the Fourier space. Okay. Now, in the radiation-dominated era, phi is basically given by the delta in radiation, not in matter. Delta in radiation will be experiencing pressure forces of radiation because radiation pressure is non-negligible. And in fact, if we work out the sound speed, which is roughly the ratio of P to rho, that will be of the, CS will be of the order of something like C by 3 or something. Okay? So it's actually it's a significant quantity. And if you put this back into the expression for xj, you will see that the gene scale will be of the order of Hubble scale. These are all order of magnitude estimates. Okay, exact numbers can be worked out. So now you see that it is very difficult for perturbations to grow because your gene scale has become like the size of the universe. So if you put this here, what will happen is we will see that the right-hand side will be essentially like going to 0. So if you do that, what will happen is if you put the right-hand side to 0, the solutions you will get. So suppose I put this to 0, the solution you will get is one solution will be log of A, another one will be constant. So constant does not grow, log of A also grows very like marginally. So essentially in the radiation dominated era, the perturbations simply don't grow. Okay. Now, this of course came from a heuristic argument. So the exact calculations will make this thing more robust and more accurate, but the basic conclusions will still hold. The other regime, which we did not talk about, was when scales are much larger. Okay, so K is really going to 0. Scales much larger than the Hubble radius. That also, it is slightly difficult to work out, but again, looking at this equation, you realize that as you make K smaller and smaller, the effect of this term seems to go down and down. Okay, so the same thing happens. So perturbations which have K values basically smaller than the inverse of Hubble radius. Remember, K is inverse of length scale. Those scales, same problem. The perturbations don't grow. Okay. So now you realize the growing of perturbations is a very a rare case in the universe. So they grow during matter-dominated era, and they grow only at scales much smaller than the Hubble radius. All other cases, they find it very difficult to grow. Now, what actually happens is this. This is again, I mean, if you think of inflation, right after, okay, suppose even if you don't believe in inflation, if you go to early enough times, what you can show is scales are of our interest are almost always greater than C by hz. This, if you have done cosmology, this basically is often called the horizon problem. So if the scales we are interested in are much larger than the horizon size at early times, then they would not have been in causal contact. Okay, because horizon size is the kind of distance light could have traveled. And if they were never in causal contact, then why is the universe homogeneous? And then you bring in inflation and other things to solve. You try to put all these scales within Hubble radius at early times. That is a separate question. But at early times, scales were indeed larger than the Hubble radius. Now, as time progresses, because of the way Hubble radius grows and the way the scales grow, what happens is scales tend to come inside the Hubble radius. Okay, so that is the first part. Now something interesting happens. If they come inside the Hubble radius, so if they are outside the Hubble radius, the corresponding perturbations don't grow. Full stop, right? If they come inside Hubble radius, they may or may not grow. If they come inside the Hubble radius during radiation-dominated era, they don't grow. They just wait. Once matter domination starts, then they start growing. Okay?
Even after matter domination, if the radiation and the baryonic matter is still coupled, like, there will still be a pressure.
Yeah, but that will be at much smaller scales. Okay, so yeah.
The perturbations will grow in that.
Yes. Yeah, that can grow. That's not a problem. Yeah. Okay, it depends on whether you are talking about the co-moving scales or the proper scales. Co-moving scales are constant. Okay. Exactly, that is the grid we wrote. Okay. Proper scales are increasing as A. Okay. Hubble, you will see, is increasing faster. Okay. So as a result, at some point, these will become smaller than the Hubble radius and going. That you can work out because we know the form of the Hubble radius. Hubble Hz, okay? And Hz will evolve differently in radiation-dominated era and differently in matter-dominated era. Okay, so all these can be worked out. So if you, again, I'm not going into the details, but if you need, we can work out, we can draw these diagrams and show what is going on. But the point I'm trying to make is there are these subtleties, okay? So firstly, if you are outside the Hubble radius, you won't grow. If you are inside the Hubble radius, But if you enter during radiation dominated era, you don't grow. You wait till matter domination starts, then you start growing. Whereas if you are outside the Hubble radius but enter in matter dominated era, you start growing right away. Okay. All these lead to this kind of feature because not all scales are growing equally at all times. In particular, this K, where the turnover happens, is very special. This is the scale which enters the Hubble radius at the matter radiation equality. Remember that A equality I wrote? So this basically is given by a ratio of omega matter and omega radiation. So for example, when we do cosmology, suppose we can detect, and that has been done, detect this turnover very accurately. And we know omega radiation because we know the CMB temperature so well. That will tell you what the value of omega matter is. Okay, so that is one way of measuring omega matter in our universe. And this, I mean, except for the omega radiation part, you really don't need the CMB angular power spectra to determine omega m. That's a completely independent omega m measurement. So that is something. So what happens is at the end, we write the power spectrum as some Pm of k equal to basically some normalization constant k to the ns t square of k. This is the conventional way of writing the power spectrum, where this T of k is called the transfer function. And this transfer function basically captures all these effects which I talked about, this entering the Hubble radius, radiation domination, matter domination, and all these things. AS is the normalization, NS is the slope, okay, power law index. The subscript S is for scalar. Okay, so what all these perturbations we were talking about are scalar perturbations. In relativistic theory, you can have vector as well as tensor perturbations. Vector perturbations are not important for cosmology. Tensor perturbations correspond to primordial gravitational waves. So none of these things we are going to talk about here, but I'm sure you would have heard about primordial gravitational waves in other lectures. So that's the thing. Okay. Why normalize? Because I remember I put up a proportionality constant, and but why do you say? I mean, there has to be something, right? It is independent of k, obviously, because all the k dependents are captured here. That gives you the shape, but the overall amplitude has to be set by some parameter, right? So no. It may depend on your inflation, or if it's inflation, it may depend on what kind of things are producing the perturbations and so on. Yes. No, it is not fixed for cosmology. Okay, so that is for our practical purposes. AS is something which is inferred from observations. So looking at the CMB amplitudes, we can infer it. Okay, so that will be one of the parameters of the model. Okay. Yeah. Yes. Okay, so firstly, equations, you can do it in whatever time coordinate you want. They are easier in conformal time. Yeah.
So it is done in
yes.
scale is C by Z.
No, Hz is A dot by A for me. Okay. Now you can define another Hubble, which is A dA d eta by A. Okay, but that is not my Hubble. Horizon is this. No, it depends again. It will depend on whether you are talking about the co-moving horizon or the proper horizon. Okay.
What is it?
So this is given T and everything else. This is the horizon. This is the proper horizon. Yeah. Yeah. No. At what point does it enter? And then what happens? Because if you have entered in radiation domination, then it is almost you haven't entered. Okay, because you are staying constant. Then it depends how much you have to wait. Now, all those modes which have entered during radiation domination, all those modes are waiting. Now, they will start growing all at the same time. Okay, so those are the relative small scales will enter first. So that is why the primordial form is more or less preserved in this part, at least in the linear theory. These all have entered during radiation dominated phase, waited, and from the matter they started growing all together. All the others, they are entering in the matter dominated phase, but different modes are entering at different times. Okay, larger the mode, it is entering late. But once they enter, they start grow. So things which have entered earlier have started growing by the time a large mode enters. So all these things are making this one non-trivial. Which one? Oh, no. So transfer function, that is convention. What happens is the transfer function, Tk basically connects to the delta. And since P has a square, so you put T square K. Okay. I mean, if historically we would have called this transfer function, that also we could have done. So that is just convention. Okay, so that is one part. Okay, so this is just a glimpse of what happens during, I mean, if you want to use relativistic perturbation theory and work everything out. So this was all about linear perturbations, and we know that that is simply not enough because deltas are growing. No matter how early you start, at some point, some of the deltas will become of the order of 1. Okay. And at that point, your linear theory will break down. So what do you do at that point? Of course, remember, we had the fluid equations written down in their full glory as long as you are allowed to work in the Newtonian limit. So in principle, we can solve them. Okay, we can solve those equations. But for example, in n-body simulations, where you are actually solving the full nonlinear problem, what do you do? So since you people are running n-body simulations, let me give you some glimpse of how the equations we wrote connect to the equations which are used in n-body simulations. So let us go back and think of, I mean, we wrote all these fluid equations in terms of densities, and then from densities we went to density contrast and so on. So let me describe the fluid in terms of many discrete tracers. So what I'm doing is I'm artificially dividing. So the fluid is a continuous thing, right? But I'm kind of artificially dividing it into small squared, what we call fluid elements. Okay. For simplicity, I'm assuming them to have the same mass, and they are at different positions. Okay. So you treat them as some point particles which are moving. Remember, these point particles are not the actual dark matter particles, not these atomic scale particles. It is just that macroscopic fluid which you are trying to describe using a set of discrete tracers. So what I can then do is I can write this quantity, let us say in terms of T and R. I could have written as sum over I. These I's are now all my tracers, delta of R minus Ri of T. So these tracers are moving. So each of these tracers, so this I goes from 1, 2, 3, 4, as many tracers as you have. Each of them have physical coordinates Ri, and they are moving. So Ri is changing with T. In each case, I am approximating them by a delta function times mass. So this has units of density, which is this. I can write in terms of co-moving coordinates, then this will be basically And I'm taking m out of the integral because I have chosen them to have all of them having x minus xi. I'm not writing, but remember the t dependence is through xi. Delta m will be basically this divided by rho m bar minus 1. And then rho m bar into a cube will give you basically rho at m equal to 0. So this I'm leaving for you to work out. Rho m0 I delta d x minus xi minus 1. This is what you will get. This is the average density today by m. So this quantity basically I could have written as 1 by number density if I want. Rho by mass is basically the number density. Yes. Now, just like you wrote an expression for the density field, you can write an expression for the velocity field as well. UTR would be basically the velocity of the particles. So what you will do is you will write, and I'm putting a subscript m. So that will be essentially given by r dot delta d r minus ri by basically I delta d. So, I mean, easier way of thinking of this up is the kind of momentum density. That is easier, but this is what you will get as the velocity field. And what you can do is you can do some manipulation. So what you can say is r dot is r is a times x, so it is a dot x plus a x dot. Put r dot back here, and you have to do some manipulation, which I'm not doing. What you will be able to show is that this um is basically given by a dot by a times r plus a times xi dot delta function of x minus xi divided by summation of delta. Just remember that, I mean, because you will have to take some, yeah, no, that's fine, yeah. Just remember the t dependence is in ri's. So this is like almost expected because this part is the Hubble expansion part. So this must be the peculiar velocity part, okay? So this one we call small v matter of t comma x. Okay. What we can also do is, if needed, this sum over delta function can be written in terms of the density contrast. Okay, so 1 plus density contrast into nm bar is the sum of the delta function. So if you needed, you can simplify that. Which one? No, you have to go through the calculation carefully. Okay, so it will come. Because these are r, these are x's. Okay, so there will be lot of things which will happen. Yeah, actually this part is easy, no? I mean, it's A dot by A and A times X, that is R. Yeah. So, and in fact, this part is easy, but there will be other factors which you have to keep track, okay? Now, all this is fine. So, what has happened is, I have gotten an expression for delta M. I have gotten an expression for Vm in terms of all these discrete tracers. I can put them into the fluid equations. If I put them into the fluid equations, that will give us equations for all these xi's, right? If I put them back. Now, what you will be able to show first is that the continuity equations is solved identically, okay? It's already contained in these equations, so it won't give anything new. The Euler equation is going to give you the equation of motion for x dot, and that will turn out to be xi double dot. So this is coming from Euler plus 2a dot by a x dot equal to minus 1 by a square gradient of phi evaluated at xi. This is the equivalent of Newton's second law in an expanding universe, written in terms of co-moving coordinates. So you see all these acceleration terms, and on the right hand side you have the gravitational force appearing, but there are all these extra factors of A which are dropping in because of the kind of coordinates we are using. You can also work out what will be the equation for velocities of individual particles, and that will turn out to be, so if I write Vi equal to A times xi dot, that will give us the equation for Vi dot. So Vi dot will be equal to minus A dot by A Vi minus 1 by A gradient. So people who have worked with differential equations, you know that even if you have a higher order differential equation, you tend to break it into many first order differential equations. So numerically, when you solve, you will be solving these two equations. X dot equal to V by A and V dot equal to this. These are the equations which are essentially solved in the code you are running. Except somebody now has to tell what phi is. So that you heard from in the tutorial itself. The calculation of phi will be essentially from this equation, the Poisson equation, 3 by 2 h naught square omega m0 delta m by a. So what you have to do is either you take the collection of all the particles, construct a density contrast from there, then put in back into this equation, calculate phi. This is numerically a challenging job. Okay, so you have to go to the Fourier space and work this out. Otherwise, this is Poisson equation. So you know its solution. All of you have done electromagnetism. So the solution will be, in this case, there will come with a minus sign, 3 h naught square omega m0 by 8 pi a, and then integral over d cube x prime x minus x prime. Potential is 1 by r essentially. And then you say that, oh, my delta m is actually sum of discrete particles. So if you put that back, you will find that this is nothing but g by a sum over I m x minus xi. Again, no surprise at all, except for factors of a, this is exactly what you expect. So you can do that, then it will be a kind of n square process. So for every pair, you have to do the this like calculate this term and then sum over. On top of that, when two particles come very close to each other, then you are in real trouble because the denominator will go to 0 and things will start to blow up. So all these things you have to account for. So all these n-body simulations, the essence is this. Okay, these equations which they solve is the technique which matters. Okay, what kind of techniques they use. They should be numerically stable. They should be also efficient. You should not be wasting too much time trying to do calculations which may not actually improve the accuracy at the end. But this is what it is. So my point was to show that these equations, which tell you, like, it's as if the equation of motion of a particle, how they connect to the equations we wrote in the morning. So these are all coming from the same underlying physics. Yeah. Again, let me iterate, I'm calling them as particles, but they are not really what the dark matter, like the microscopic level, what is made up of. In fact, the box you are running now, you should go and try to compute the mass of each particle. You know the size of the box, right? That is 50 H inverse co-moving megaparsec cube. That is the volume. You know what will be the total mass in that box, assuming the average density to be the average density of the universe. Okay? That box, the matter in that box, you have divided into 64 cube particles. So divide that total mass by 64 cube. That will give you mass of each of these particles which are moving inside the box. And I guess that is something you will plot when you visualize. Okay? And that will tell you. So that essentially sets the resolution of your simulation. So now if you want to like go to smaller and smaller masses so that you can resolve better, you have to essentially pay more. I mean, in the sense you have to go for a higher compute because you have to increase the number of particles, or else you have to compromise on the size of the volume of the simulation and so on. Okay, so fine. So that is all about how you do simulations. Now, as I said, simulations are basically where you are solving the nonlinear equations in its full. And remember, when you put these ones back to derive this equation, don't put it in the linear version of the equations. Put it in the nonlinear version. Only then you will get the correct equation. So these are fully nonlinear equations. No linear approximation have been made. Now I'm going to make linear approximation at this level and see what does it tell us about particle trajectories if I am in the linear limit. Okay. So particles are in your simulation, particles are probably moving in a very complicated way. If you had have saved the snapshots, you could have actually tracked these particles, but that is a separate thing that would make the whole thing very expensive. And you will see they move in a non-trivial way. What I'm asking is, if I am in the linear limit, how do the particles move? We know how the densities evolve, but how do the particles move? So to do that, let us again go back to, for example, the Poisson equation. Okay. So we had the Poisson equation, which was written in terms of phi. Okay, it is probably already somewhere. I define a new potential. So I call it psi. And I'm doing it, this is a definition, 2 by 3 h naught square, omega m 0, a by d plus phi. If I put it back in the Poisson equation, I will get del square psi equal to delta m by d plus. just remember the Poisson equation is, even in the nonlinear regime, it's linear. Okay, so this is the full Poisson equation. There is no approximations as yet. However, if you are in the linear regime, you know that delta m will grow as d plus. Okay. So in the linear regime, psi will be essentially constant in time. It won't evolve. Of course, in matter-dominated era, d plus is a, so phi also won't evolve. That we talked about in the morning. But even if you are not in matter domination era, as long as you are in the linear regime, psi will be constant. So what I can write is psi, which is a function of Tx, is some psi naught of x. Okay. The psi naught is entirely determined by the initial conditions. Whatever initial conditions created the field of our universe, that is that. Okay. And it does not evolve as long as things are linear. So if it is linear, now I put this back into the velocity equation. Where is the velocity equation? This is the velocity equation, right? So I put it back here. So I will get Vi dot plus A dot by A Vi equal to minus 3 by 2 H naught square omega m d plus by A grad of psi. And when I write grad of psi, let me as well write it as grad naught psi evaluated at xi, because psi is not evolving in the linear regime. That equation held for linear as well as nonlinear regime. This equation is only for linear regime because I have put psi equal to psi naught. Okay. In the linear regime, we also remember how V evolves. So keeping that in mind, let me put an ansatz, which is like Vi equal to A d plus dot into some Ui, where Ui doesn't have any time dependence. Why? Because all the time dependence of V is in this A times d dot term. How did I get that? Because I solved the linear evolution in the previous lecture. You put this back. So what you end up is getting Vi to be minus A d plus dot gradient of psi naught. So this is how the velocity field will evolve. Okay, that's good. So how will the trajectory evolve? Trajectory is what? Xi dot equal to V by A. So then Xi dot will be equal to minus D dot. This does not depend on time. So then my solution is Xi equal to some initial condition Qi minus D plus so if you think of D plus as some kind of a time coordinate, a proxy for time, then this is essentially particles moving in a straight line, okay, with constant velocity. Okay. X equal to initial coordinate minus t into velocity. So this is how particles move in the linear regime. Okay, they move in straight lines when interpreted in these coordinates. Now, some of you were asking how the initial conditions are set. To a very good approximation, this is what is used. Okay. So you will set up a position grid at the initial time. This could be as early as you want. And let us say you put all the particles, this is a uniform grid, although the way I have drawn it doesn't look uniform. But let us say you put the particles exactly on the grid. If you leave it like that, nothing will move because all forces will cancel. It's perfectly symmetric. So you have to give them some kicks in the beginning. Those kicks cannot be random because they should satisfy the linear theory at that early time. So what you do is you give kicks based on exactly this term. Okay. This will ensure that whatever you get is consistent with linear theory. You have to make sure that these kicks are not too large. So it should not like this particle goes and comes somewhere here and that goes somewhere there. It is clearly linear theory. You are going beyond linear theory. So that is why you have to set things up early enough so that this part is small. You give that kick, then put that back into those equations and let them run. Okay, that is your n-body simulation, the basic crux of it. Nowadays, what is done is, okay, instead of using simple linear theory, people often use the second order perturbation theory to make it slightly more accurate. But those are details, but the essential idea is this. But even with this linear theory, now we will see that we can do a lot. Now, what we can do first is, see, this gradient is in terms of x, and this is xi. What you can show is that this gradient, delta with respect to x of psi naught, which is xi, to the linear order is gradient of q with respect to psi naught at qi. What I'm doing is I'm saying that as if there is an implicit coordinate transformation between x and q. So I'm going into q coordinates. So the difference between x and q is this quantity, okay, which is small in the linear limit. So you will be able to show that the derivatives will be equal to this and the higher order terms will be second order in psi naught. Okay, that is the difference between q and x. So if this is indeed the case, then I write this as qi minus d plus gradient of psi naught qi, gradient with respect to q. So what is happening is, this equation was a bit non-trivial in the sense, suppose I want to solve it, I have the initial conditions, but if I have to get xi, it is as if I have to know the potential at xi to start with. But at the linear regime, you can replace this by calculations done at the initial coordinate itself to a very good approximation. Now this can be solved. Okay, right hand side is in terms of initial conditions. As long as you know the initial conditions, this xi is solved. These qi's are what are known as the Lagrangian coordinates. Okay, so what happens is now you can identify particles through their initial positions. Till now, I was identifying particles saying that, okay, this is particle 1, particle 2, particle 3, and so on. Rather, I will say that, oh, this particle, let me identify it by its initial position, wherever it was. And this one, I will identify it by the initial position. So I can basically drop the I and write this equation as x, which is a function of q, which is q minus d plus delta q psi dot. This is a standard practice in fluid mechanics where you basically try to work out the trajectory of the particle given its initial positions. And those are, so here what is happening is, so again, since we have come this far, when we were writing equations, those fluid equations, those were basically fields as a function of x and t. So it is as if you are sitting here and you are saying how the fluid is moving. So the delta or the density and velocity in front of you are changing. In this picture, you are sitting on the fluid particle and moving with the fluid particle wherever it takes. Both the descriptions are equivalent. One basically follows from the other, and both have their own advantages. The n-body codes you are running follows this picture. It's following the particles, basically. You could have also written an n-body code using Eulerian coordinates. There you will divide the box into grids, and in each grid you will solve those fluid equations. Both have their advantages and disadvantages. For collisionless matter, the n-body codes based on Lagrangian formalism are more popular and more useful as of now. This way of getting the position of the particle given initial positions is known as Zeldovich approximation. There is an apostrophe here. Zeldovich approximation is very accurate in the linear limit. I mean, it's derived from linear theory. But what people have done, including us, is to just evolve the system using Zeldovich approximation, even when we know that linear theory is probably not holding. You can show that in this kind of n-body codes, for a long time, as long as you are interested in relatively large scales, Zeldovich approximation gives you very accurate results, even when linear approximation has broken down. Okay, so that is the kind of, that is why it is called approximation, because till now the linear limit there is no approximation, it's a linear approximation, but Zeldovich basically suggested that you can just take it forward beyond linear theory. From Zeldovich approximation, you can deduce several properties about structure formation, which are interesting. Okay. So let us try to see what it is. Think of Zeldovich approximation as a kind of coordinate transformation. So as if initially particles were here with some coordinates, let us say t initial, these were their coordinates, I called it q. And at a later time t, they moved somewhere else, but I can map them, okay? So something is mapped here, something mapped there, and so on. So these are my x coordinates at some time t, and the coordinate transformation is essentially this. The t appears through this d plus, okay? D plus is a function of t. So writing this as in the component form, let us assume I am using Cartesian coordinates. I can write x alpha to be q alpha minus d plus del psi naught del q alpha. Alpha is your x, y, z, or 1, 2, 3, whatever you want to call it. Now, because, I mean, now imagine a small volume. For example, you have initially a small volume of d cube q, and that went to d cube x. Now, what will happen is there will be some, the mass within these volumes have to be conserved because every q is mapped to some x. And if that is indeed the case, you can relate the rho at the initial time to rho at any later time. And how will they be related? The idea is simple. So let me just try to write it again. Rho m at time t, written in terms of position, the x, which are also function of t and q. A cube d cube x. Why did I write a cube d cube x? Because this is the proper volume. Is rho initial written in terms of Q A initial cube B cube. Okay. No, this is conservation. This is the equation. Jacobian will be the next step when you want to write rho in terms of rho initial. Okay. So now if you want to write rho m, let us say as a function of tq, this will be A initial cube by A cube rho initial of q. Sorry. No, it's not. Here comes the Jacobian. Yeah, that's it. This is your Jacobian. So basically, if somebody gives you the initial configuration, you can find out the density at a later time, provided you can calculate this Jacobian. How will you calculate this Jacobian? You know the coordinate transformation. So you can calculate the Jacobian. So what does this give actually? So you can work out this del x alpha, del x beta, del q beta. The first one will be some Kronecker delta, and this one will give you the second derivative of this initial potential. So you will end up with something which looks like this. Rho n will be, this is just remember basically the fact that rho is evolving as a cube. So that is the extra scaling which is appearing here. Rho initial of q and the Jacobian of this matrix, which is delta AB minus D plus del 2 psi del or B, I'm saying alpha beta, right? Alpha beta, alpha beta. So you have the initial potential. What you do is you take second derivative at every place. You work out the effect of this Jacobian, and that will give you the matter density at any later time. If this quantity is very small, that is the linear limit, you will be able to show that this will become, so in the linear limit, this one will essentially become A initial cube by A cube, rho initial cube, 1 plus D plus del square psi naught. So if you write down this full determinant and then ignore all the second order terms, you will end up with only the diagonal terms which will matter, and it will be del square. So this is exactly what you expect in the linear limit. That rho will be some background term which does not depend on time, and there is a part which is growing as D plus. This is the density contrast part, because they will be second order in psi naught. Right? However, as I was saying, Zeldovich suggested that let us go ahead and apply this. Let's not worry about this limit, okay? Keep all the terms, whatever is coming. Yeah. Then something interesting happens. So this is a determinant of a matrix, right? What I can do is I can take that matrix, basically I can diagonalize it, okay? So the determinants will be basically products of the eigenvalues. So let us say that the eigenvalues of, so this essentially is a tensor. Let me just write it. This is known as deformation tensor. If you think about it, one derivative of psi naught gave you the velocity field. Okay. Another gradient will give you tidal effects. Okay. So as a result, it's called the deformation tensor. Okay. How this initial volume element, how that gets deformed as the universe expands. Let us say it has three eigenvalues. I mean, it has three eigenvalues. Let us call them lambda 1 of q, lambda 2 of q, lambda 3 of q. Remember, at every point, the deformation tensor will be different. So these lambdas will be different at different points. But every point you will get these lambdas. So in that case, this will become proportional to, I'm leaving all the details out, but it will be something like 1 minus d plus lambda 1 q, 1 minus d plus lambda 2 q, 1 minus d plus lambda 3 q. Suppose we order it in such a way that lambda 1 is greater than lambda 2, greater than lambda 3. I just define it in such a way. And suppose, let us say that lambda 1 is positive. It can happen that all three are negative, but suppose at least lambda 1 is positive. Then what will happen is this d plus lambda 1 initially will be very small because it's basically coming from this quantity which is supposed to be small. But as d plus is increasing, this quantity will keep on increasing. At some point, this quantity will hit 1. The moment this hits 1, your rho goes to infinity. Physically, what happens is, this is your deformation tensor. So your volume had some form. You said that I will, like, these eigenvalues represent like three principal axes of this deformed volume element. What this is saying is, along one such axis, this thing has collapsed. It has collapsed to kind of 0 there, and the density has gone to infinity. Now, if you think of an arbitrary shape and it collapses along one direction, arbitrary 3D shape, and you collapse along one direction, what you will end up is something which looks like a sheet. So Zeldovich predicted that initially the structures which will be formed will be sheet-like structures, or he called them pancake. Okay, and that is indeed what you see in simulations. Okay, this one axis like collapses, you form sheets. If there is a point where lambda 1 and lambda 2 are equal, then two axes will collapse almost simultaneously. Then you will end up with something which will have one kind of dimension. That will be a filament. The third option is when all these three are equal, then all the three axes will collapse. You will form a halo. The thing about this kind of idea is that suppose somebody gives you an initial field, okay? You will work out, you can work out this quantity, you can work out the lambda ones, and then you can go to each point and see what kind of structures they will form and when, okay? You will know, given the value of lambda 1, you will know at what rate shift this will become 0 because you know how d plus evolves. So this is an idea which like attracts many people in cosmology, where you say that can I predict what is going to happen to the universe just given the initial condition? I don't have the kind of resources to run a full n-body simulation, or I want to do it very quickly, okay? Let it be slightly inaccurate, I don't mind. But I just want to know where the halos will be formed, just to give an example. So Zeldovich initially gave an idea of how to do this. And we will see throughout the lecture that this idea is constantly used in cosmology, including even today. That if we can, like if there is a problem where I don't want to run the full simulation, can I just guess something just from the initial condition about where the galaxies will form and maybe create a map or something which can be compared with the galaxy observations. So this is essentially the idea. So clearly, Zeldovich, I mean, when rho goes to infinity, that is definitely not linear, right? So clearly, Zeldovich already gave us something which was based on linear theory, but which took us beyond linear theory. And now, as I was saying, this is like only using linear theory, meaning first order perturbation. What you can do is you can use second order perturbation, and these are essentially called Lagrangian perturbation theory, LPT. So Zeldovich is one LPT or just LPT. Then you have 2 LPT, 3 LPT, and so on. 2 LPT codes are very common, and they are often used for setting up initial conditions for n-body simulations. But you can also run them for other things as well. Okay. Yeah. This one, yes. Yeah. I mean, yes. Yeah. So these will be the eigenvalues of your tidal tensor.
Plus delta. You might not have got the pancake and delta.
No, that is the thing. Because you wrote it in this way. So what you did was you took the whole thing in the denominator. And that happens because you are working in Lagrangian space. So this is where Lagrangian space helps, makes the difference. Exactly. Yeah. So if I had written this, then no pancakes, nothing. Okay, it is this. So this is something somebody would have to like really understand, that writing in this way gives you something more insightful. And that's what Zeldovich did. Otherwise, linear theory was known. But people from linear theory, you cannot know that sheets and pancakes will form. Yeah.
But it is a symmetric matrix. So when you go to the eigenspace, those q and etc. directions are there. I mean,
Yes, yes. So different points will have different directions. Exactly. So different points the sheet will form in different ways if that point forms sheets. See, there will be some points where nothing may form because all the eigenvalues may be negative. Okay, so they are probably voids.
statistical thing, right?
It's a statistic.
Predict without which direction the theta and phi into.
A priori, no. But suppose I give you the initial condition, which is easy to generate. Then in the initial condition field, you can work this out. That is the, yeah. Of course, Zeldovich and after that his collaborator Shannarin and all worked everything out analytically just from this. No, I mean, and they could predict how many halos will be formed at what redshift. So there is a lot of work which went on. But nowadays, you can also see that n-body simulations are not that expensive also. You are all running some, okay, it's not a very cutting edge simulation, but you are all running and they are all publicly available. But there are still problems where running n-body simulation is not viable, and these LPTs are often very useful. We, for example, in our research use them quite often. And again, I can tell you why, but that is a separate thing. Now that is one application, okay? So let me again go back there. And I will do one more thing and stop today. That is spherical collapse. So till now, what we have been doing is linear, and Zeldovich, you can call it quasi-linear. Okay? I mean, you have gone beyond the linear theory and you got something, but it's still not fully nonlinear. Of course, the fully nonlinear thing, you have to work using n-body simulation. But there is one case where the full nonlinear theory can be worked out, that is spherical symmetry. Okay, that's called spherical collapse. So spherical collapse is you are basically considering a spherical shell of radius r, which is a function of t. This is, remember, proper radius, not co-moving, which is evolving with time. Okay, and so this is your shell, and it encloses a mass m inside it. Okay, and that mass is kind of conserved. So, suppose you want to find the equation for r. So till now, whatever we have derived, you can use them because you know the equation for x dot, right? For any arbitrary like configuration. So what you can do is you can say that I will choose my initial conditions such that these points lie on a spherical surface, and I will put that equation, that configuration into this x and work out what that evolution of the radius will be. So one way of doing it is you say that my xi is nothing but RT by AT times A initial by R initial times QI, where QI mod is R initial by A initial. So what we are saying is that at initial time, I have put all the QIs at some radius which is R by A. Why did I put R by A? Because this is in co-moving coordinates. So if I multiply by A, I will get the R initial. And at any later time, it is given by R by A. Okay, because this, if you take mod of this, it is R by A. So this is, I'm putting a very specific configuration and trying to see what will be the equation of motion for this. So basically now what I have to do is I have to use this, put it back into the equation of motion. And what you will find is an equation which is r double dot equal to minus gm by r square minus 4 pi g by 3 rho rest bar plus 3p bar rest by c square. I'm not deriving this. It's not very difficult. Try it. If you get stuck, you let me know. But at the end, this is quite obvious. So r double dot equal to minus gm by r square is exactly what you would have expected from Newtonian theory. This part is coming from all the other elements because they can contribute to that phi. If you are talking about lambda CDM universe, then that rho rest, you know what that rho rest, and so this whole thing will become essentially h naught square omega lambda times r. Basically, this minus sign come with a plus sign because of negative pressure. So firstly, you see this lambda comes with a positive sign. So that is that famous repulsive kind of gravity of lambda. But more importantly, at smaller r's, it is not going to be important. So if we are interested in a spherical region which will eventually collapse, let us say, then this lambda can be ignored. It is not necessary. You can work this out with lambda put in. The equations will be more complicated. So what we will do is we will stick to the matter dominated regime for the time being and put lambda equal to 0. So then this equation is r double dot equal to minus gm by r square. You probably would have solved it first time in your 11th standard or something like that, when you threw a ball and it went up and came down, and then you probably calculated the escape velocity and other things. It is that same equation which appears here. So solutions are pretty well known. It is just how you interpret the solution is where we are going to spend some time. So what we will do is we will have to first set up the initial condition. So what we will say is at very early times, some a equal to a initial, the shell was expanding with the universe. Basically, it was following the Hubble's law. So, I mean, very small deviations from the Hubble's law. Okay. And at early times, this is a good assumption, of course. So, the r dot at that early time was h at that early time times r. I mean, obviously, there was some deviation because otherwise it won't decouple. But that is to a very good approximation. This is what it was. Any deviations were very small. Now, suppose I calculate the density contrast of this region. This region, the density contrast will be rho. So, rho will be 3m by 4 pi r cube t. M is not changing with time, right? Then 1 by rho m bar time minus 1. And if I write the rho m bar in terms of omega and other things, it is 2 gm by omega m naught h naught square a cube by r cube minus 1. I know how A is evolving, right? A evolves as T to D 2/3 in matter-dominated air. I hope you have done this. Okay. Otherwise, just put it in the Hubble, the Friedman equation, and you will get this. So this tells you that A dot by A is 2 by 3. Then this just becomes 9 gm by 2 t square by r cube minus 1. So this is how the density contrast evolves with time. And now we will put in the solution and see what happens. The solution to that equation r double dot equal to minus gm by r square is the so-called cycloid solution. It does things like this. So we are interested just in one cycle. So basically, it will start from somewhere, it will go up and come back. This is how it looks like, r versus t. It will go to a maximum radius and will fall back. For this to fall back, you have to make sure that the equivalent of escape velocity, the velocity, initial velocity is less than the escape velocity. Or in other words, if you think of that as a problem like a particle moving in 1 by r square, 1 by r potential, then this will be like the energy has to be negative. So otherwise the system won't be bound. So if I write down the energy, it's like half r dot square gm by r initial. This has to be less than 0 for this to happen. Otherwise, there will be cases where it will keep on expanding with the universe. You know what r dot is, so you put this back here, you end up with something where E will be essentially given by E equal to minus Gm by R initial delta initial. This is the energy. So basically just put in r dot from here and manipulate a bit. So what does this tell you? What condition do you need for this thing to go up and collapse? Anyone? Physically, what would be the property of this region for it to go expand and then collapse? What did you say? Why? Delta should be greater than 0. We want E to be negative, so delta should be greater than 0. Right? So there is no radiation, no pressure. We are talking about dark matter, collisionless matter. So overdense regions will expand and at some point will not expand anymore and will come down. The universe will keep on expanding like this. So if it was expanding with the universe, it would have probably gone like this. But here, this is what happens, and overdensity is crucial. Again, it is not surprising. You need like more mass than average for it to collapse. That is kind of, so that is gravitational instability which I was talking about. Now let us go quickly. Let us write down the solutions. You can, so R is this. You can write only in parametric form, B theta times sine theta, where A is Gm by 2E and B is Gm by 2E to the power 3 by. Again, these are basically solved equations. The thing is, I can put this back into the expression for the density contrast. And theta will basically go from 0 to 2 pi. So delta will be given by 9 by 2 theta minus sine theta whole square by 1 minus cos theta whole cube minus 1. Now you see, things have cancelled out in such a way that the density contrast does not depend on the initial condition, it does not depend on the mass or anything. It only depends on theta. So any property of the system which is determined by the value of theta will be independent of the mass of the system or what density contrast it starts with. What kind of property can we think about? For example, when does it go to the maximum and turn around? So this is called turnaround. Turnaround will happen when R is maximum. When is R maximum? What value of theta is R maximum? Theta equal to pi. So at theta equal to pi, the system will turn around. Now when it turns around, different systems may have different radii, okay, because that will depend on all these G, M, E and so on. However, when it is turning around, the density contrast will be the same for all the systems. That will be essentially what you get by putting pi here. So no matter what mass you choose, no matter what initial conditions you choose, no matter at what time it is turning around, but when it is turning around, the density contrast will be this way with theta equal to pi. I will let you work this out, what that is. Okay. So you'll find that it is of the order of 5. Okay. So now for the first time, we are getting a feel for what kind of densities are we talking about when things starts to kind of decouple from the universe and start to like collapse. So few density contrast. Yeah. I will come to that. So theta equal to 0 is like t equal to 0. So t equal to 0 anyway, we don't know what has happened. So we will start at some theta where r is small, right? Because at very early times, it is not even a matter-dominated universe. The baryons haven't formed.
Physically, is there a motivation?
No, physically, these approximations break down. Okay, that is the only thing. So you cannot take the equations. So theta equal to 0 is easy to understand because at t equal to 0, we don't know what went on. Okay, so we have to start at a reasonable time. Theta equal to 2 pi is interesting and coming to that. Okay. So the next thing is what happens at theta going to 2 pi. Theta going to 2 pi will make r going to 0 and delta going to infinity. So it is telling you that if the spherical shell remains spherical throughout, it will basically collapse to a black hole, which is not surprising. But in reality, what happens is, so what we are saying is these particles can only move in radial directions. Okay? But in reality, even at early times, statistically speaking, some of them, all of them, will have a small bit of non-radial or tangential motion. That won't be important at early stages. So things will follow the spherical evolution for a long time. But eventually, as it collapses, the velocity increases, these tangential motions will also get amplified. And at that point, you cannot use all these simple formulae which we have been using. Okay, things will go out of hand. The moment the tangential motions become comparable to radial motions, this approximation breaks down and the system becomes truly nonlinear. It goes through series of processes. This is something called violent relaxation, which happens in collisionless systems. And eventually it will virialize. So it will achieve an equilibrium where its properties are determined by virial theory. This is a state where any like gravitational pull is balanced by random tangential motions. So that is some relation between kinetic and potential energy that we will work out. So what happens is when you apply virial theorem, basically you can show that the kinetic energy is negative of potential energy by 2 and energy is basically u by 2. Then what happens is, and u is negative obviously. So if you put this back, what you will find is a relation between mass and radius, and the time of virialization will be corresponding to theta going to 2 pi. So you can work out what the time of virialization would be. It will be 2 pi b, where b is given by all these conditions which we talk about. And you can work out r virial. So basically r virial will be A. That comes from putting the energy to be equal to u by 2. So this you will say is minus gm by 2 r virial. So once you put these things back, what you will find is that 1 plus delta at virialization will be given by 18 pi square, which is roughly of the order of 178. These are all done in very like idealized situations, but this also tells you something, that when a halo forms, its density or its density contrast is of the order of 200. Okay, it may not be exactly 18 pi square for a realistic system. But till now we did not have any idea whether it is 10 or 1000 or what. We're talking about this kind of density contrast when the halo forms. There is one final thing which is useful for spherical collapse. That has to do with the fact that suppose I had worked everything using linear theory, what would have happened? Of course, there won't be any collapse. But suppose I like close my eyes and say that I will solve the system using linear theory. I don't care about the exact solution. Okay. So then what I would have done is, so for example, I take the limit t going to 0. At early times, I know linear theory holds. There is no doubt about that. So when theta goes to 0, what I know is I can write the expression for density contrast. It is 3 by 20 theta square. Where did I get it from? Because I know delta in terms of theta. You put theta going to 0, do a Taylor series expansion. This is what you will get. This also you can write as 3 by 20 6 t by b to the power 2/3. Can someone tell me, does this t dependence for linear density seems reasonable? What? Because of matter dominated what? Why should it be t to the 2/3? Good. A grows as t to the 2/3 in matter dominated era. We have also seen that delta grows as A in matter dominated era. So this is correct. It's a sanity check. Okay. Let us call this delta L of t. Now delta L of t is what? I'm saying delta L of t is 3 by 20 6 t by b to the power 2/3. This is delta linear of t. At early times, delta linear of t will be the true density contrast, because the true density contrast is given by linear theory. But at later time, it won't be, because delta will move away from linear theory. But suppose I did not know, I was solving everything in terms of linear theory. Then what will happen is, at collapse, so when t equal to t virial, we know that t virial is 2 pi b. Delta linear at virial will then be 3 by 20 12 pi to the power 2/3, which is 1.686. Now this is very interesting. What this is telling you is, suppose somebody gave you some initial condition and you started evolving it using linear theory. And you did not care, you did not stop even when delta became of the order of 1. You said that I will just evolve it using linear theory. Anyway, I can evolve every point independently. Now you know, the moment some region in that linearly evolved field picks up density contrast equal to or greater than 1.686, that region would have collapsed. Of course, assuming that spherical collapse is the correct way of collapsing things. This is again very powerful. And as I'm constantly saying, cosmologists are always interested in working out things just from the initial condition without actually running the simulation. This gives you one handle on that. You go to the initial condition field, evolve them linearly, but that is trivial. It is like scaling everything by the same number. And you find out at a given redshift of your interest, which points have kind of crossed 1.686. This is just a universal number. It does not depend on any condition. And you say that, oh, this point, that means I know, would have collapsed at that redshift. There are some subtleties, and how this is used to calculate like properties of collapsed objects will come up in the next or next to next class. But this is an idea which is constantly used in cosmology. Okay. So fine. So this is where we will stop today, and yeah, we will take more complicated things from tomorrow. So till today we have been only talking mostly about time evolution. Tomorrow we will talk about the statistical properties. How are things distributed spatially?